Great, thanks Joe, and thanks to all the organizers for inviting me. I'm going to talk about a model called deep Gaussian processes, which is something we've been working on for a while, which is very much inspired by the sort of ideas in the deep learning community. But what I thought I'd do is start with a bit of background and perspectives, because I think that these models aren't sort of things that necessarily people who've come into the community recently would be that aware of. So I wanted to try and motivate and perhaps give us a 30,000-foot point of view from what's going on. Then I wanted to sort of say, well, why? So I think all these, convolutional neural networks are great, but I think there's a class of problems where we don't have solutions yet. I think other people agree with this, and one of those domains I call massively missing data. There I'll sort of briefly show some results with deep Gaussian processes and some theory about how they work. Okay, so I came into this workshop yesterday. I see it's a bit sparser today, but it was really, really full, and I thought immediately, oh my God, the community has ate itself. What do I mean by ate itself? Well, I wasn't sure, so then I thought about it for a while. So I look up eating itself, and it's called Ouroboros, this snake. And it's designed to sort of represent some eternal life or whatever. But what I think is going on at the moment is convolutional neural networks that I actually got into machine learning while I was working on oil rigs in the North Sea, and I used to implement neural networks in C++, Bull and C++, sitting on an oil rig. And that was like 1995. So we're now revisiting these models from 1995, but we're revisiting them with a lot of new ideas. We've recently, before this, revisited Boltzmann machines. And I think there's a lot of interesting stuff there, but we seem to be sort of shifting on. Now, by my recollection between these two things, there was something else called Gaussian processes. So my forecast is our head is going around here, and it's going to start consuming Gaussian processes again. So I wrote this down, and then I had a sudden follow-up thought, and I realized this. This isn't a new phenomenon. So Boltzmann machines were first around in 1980, and actually not convolutional neural networks, but neural networks go back to the sort of 1960s, Rosenblatt's perceptron. And Gaussian processes, a lot of the work was done in the 1970s. I don't think that this is necessarily unhealthy, but I think it's always worth having context and thinking about these sort of things. Now, why, in my experience, did we move from convolutional neural networks to Gaussian processes? People like to talk about a neural network winter and this sort of thing. I think it's part of it is a social phenomenon. It wasn't that people, what actually happened was people got good results with models that were easier to understand from the modeling side. And people moved to those models because if you could understand the model better and get as good results or better results, then that was seen as a good thing. I think that the change recently has been we've got a lot more data and a lot more compute. So actually we're able to worry less about the statistical side of the modeling. I'll try and clarify what I mean by that in a second. And just worry about trying to scale up the models. And I think we see a lot of that in the community, that people are sort of interested in how you get the algorithmics to scale, how you handle very large data, how you fit these models. But I think there will always be merits in going back to these sort of Gaussian process approaches, because I think, personally, I believe they're statistically a lot more efficient in terms of that you can get a good result with less data, and I'll hope to demonstrate that. So the thing I want to emphasize that I think is not often enough emphasized, in fact, I think I'm the only one that says it in the way I say it, but maybe I don't say it in a good way, is the separation of model and algorithm. So if we think of the talks that we saw yesterday, I'd say they tended to focus more towards the algorithm. That's from my perspective of what model and algorithm is, which I'll try and describe. And I'm going to focus more on model. So what do I mean by model? I'm saying model is encoding our beliefs about the regularities of the universe. So clearly that's going on in a convolutional neural network because you're getting invariances. You're encoding them in the system. And what you want to do is you want to combine the data you have with your model, which gives you the regularities of the universe, to make your prediction. Now, neural networks are working really well. And I really like the way people are starting to plug them together as different components to get an overall solution. So we're sort of saying, oh, I've got a recurrent neural network here and a convolutional neural network here, and we're plugging these things together. But they're actually quite complex entities as models. So when I say complex here, I mean in terms of how easy to understand, in terms of what's going on, in terms of what it's saying about the data. However, they have very simple algorithms, relatively speaking. Certainly when I first got into neural networks in 1995, the appealing thing was you could write down these learning algorithms very, very quickly and get going. You didn't have to know an enormous amount about linear algebra, probability theory, or anything else. You could just get an implementation going. Now, I'd argue with Gaussian processes, you've got something quite the opposite way around. I'd say with the Gaussian process, it's a very simple model. I don't mean simple in terms of complexity. It can represent an enormous number of things, but it's simple to understand from a mathematical perspective. But the algorithms get quite complex. So fitting the models is quite complex. I think a lot of the appeal of the sort of deep learning neural networks is in the simple algorithms. I think models with simple algorithms always win through because people can access them much easier and implement them very quickly. But there will still be merit in going for more complex algorithms because you get a better mathematical understanding of the model. Okay, so I actually wrote a little bit about that on a blog post that I put into there. And today the talk I'm going to focus really is on the modeling side, or trying to give you intuitions. I'm talking at the large-scale kernel machines about part of the algorithm later on. There's too much stuff to give in one talk about the algorithm. So why might one think that there's an alternative approach to convolutional neural networks? Well, this is a result that surprised me. So this is work by Chao Lu and Zhao Tang in Hong Kong University. And we had Chao visit after he did this work and talk about this work. This was the first paper to outperform humans on the cropped version of the learning faces in the wild data set. I think if you don't crop these images, humans still win. But if you crop these images to the face, the first algorithm to outperform humans was actually based on a Gaussian process. Based on a Gaussian process latent variable model, which is a model I developed, but I wasn't involved at all in this work. So this curve here is the ROC curve, the red dotted curve for what they called Gaussian face, which was the work by Chao Lu. And it significantly outperforms both the humans and the previous best performing, which was deep face, which I think is actually deployed within Facebook now, looking probably in some evolved variant. Now, the most interesting thing about this result is that the Gaussian face model used, I think, 100,000 training faces, and the deep face model used 1 billion. A further aspect of this result, which is very interesting, is my understanding is, there may be people that certainly can correct me in questions later, is that deep face actually takes these faces, projects them onto a 3D model, and does a transformation to flatten the faces out before using a convolutional neural network. And in Gaussian face, Chao told me that he doesn't do any of that. He just takes a box and just flattens it out. So something's going on, very significantly different in terms of what Chao did. That was a really impressive result for me because we haven't managed to get these things to work at such scale yet, only 100,000 training data, and that's the sort of real objective of ours, but for someone else to do it was pretty cool. So the core component that actually Chao didn't use the thing I'm talking about today, which is deep Gaussian processes. What he used is a Gaussian process latent variable model, which is like a shallow Gaussian process, on top of a large amount of feature engineering, part of which was to use a deep neural network for extracting features. So there's convolutional stuff going on in there as well, as I understand. So it's a paper at AAAI. Now, but the core component at the top that Chao implemented that was different was a dimensionality reduction based on Gaussian processes. So today my understanding is the shift is more towards unsupervised learning. So in this context, so I do have slides where I talk about these models as supervised models, but I've tried to shift this more towards the unsupervised context. So we're trying to model data y with a vector value function that maps from x to y, where x is an unknown latent variable. So this is how I view unsupervised learning. And what our aim is to put a prior distribution over x and integrate it out. So this vector valued function In Gaussian face, the latent variable model uses a Gaussian process to handle f. Now, what does that mean? Well, it means instead of parameterizing f, which would be the typical way one does in a neural network, and optimizing the parameters, you actually have a prior distribution over the class of functions you expect, and you integrate them out. That's very powerful because it allows you to do a lot of extra things like structural learning, so on and so forth. Now, they didn't actually use the most powerful version of this model we have, but they were scaling it to 100,000 data, so that's not that surprising. It's sort of an older version. It actually dates back to work we did in sort of 2003, I think, the version they used, with lots of modifications to scale it up to larger data, and a discriminative nature. So another thing Chow did is he used a sort of approach where you add label information to the latent variables. Okay, so what's the problem with this type of thing? Well, these are very powerful models. Gaussian processes allow nonlinear mappings. What we're trying to do is take some sort of low-dimensional space and map it with a nonlinear function to some sort of higher dimensional space. The belief is that you can model data in this way. But the problem is that if you try and propagate a probability distribution through this nonlinear mapping, you tend to get something very intractable. So what I said here is we've got this nonlinear mapping, but we need to put a prior over x. And as soon as you do that, you get a very powerful class of models and a very intractable class of models. So this is an illustration of that. So this is just taking a Gaussian density. We very often use Gaussian priors in the latent space and mapping it through 1D to another Gaussian density with a sort of a, actually this isn't a Gaussian process mapping. This is, I used a little RBF network, an RBF basis here. But you get something very complex and multimodal. Something, in fact, you get, if you use a Gaussian process, you get a non-parametric density estimation in 1D, a very powerful one. So that's already interesting if we actually don't even do dimensionality reduction. But the motivation when I first looked at this was always with dimensionality reduction in mind. Now, by way of illustrating, there's a weird facet to these models which I don't really have time to explain the theory. So I was going to just try and illustrate this idea. In fact, I've got the video here. Oh, that looks slower now. Hopefully you're not all using the internet. Everyone stop using the internet. So this work here is using Gaussian process latent variable models. This is work by Bill Baxter, and I can't remember the name of his collaborator, Bengio, from 2006 at Eurographics. Now the data set here is, so we're faces again, but it's line drawings of faces. And what these guys did is they take those line drawings of faces and they're turning them to a vector representation, high dimensional vector, something like 100-dimensional vector. So that's Y. Now, he's fitted a Gaussian process latent variable model. What he's doing here, let's pause that and try and describe. So this space here is his X space. So in dimensionality reduction, he's got a two-dimensional space, and what he's building is a tool for assisting animators. So what he said is, I'll make the low-dimensional space two-dimensional, and I'm going to use a map. Well, what he's showing is the generative model from that two-dimensional space to, on the right, what we see here is the generated data Y. Now, there's some challenges in this data set because there's a correspondence problem. He's got 4 data points, 4 drawings he's made. Each of these drawings is projected into the latent space noted by these symbols here. So that's the X location. But he needs to work out the correspondence, the features from the lines. So there's a little bit now where he's doing that. But actually, while he's doing that, so you'll see that the face lines move across the face because the correspondence is wrong. So he's fixing the correspondence there. So that's a detail that's nothing to do with me and something Bill implemented. But the learning was done. Bill downloaded code from my website in C++ to implement this, debugged loads of it for me, which was great of him. And now, look at this. You've got 4 data points, and you've learned a nonlinear manifold that can project from 4 data points up to hundreds of dimensions, generating new images. That's really unusual. People don't think you can do this, and you can. It's very elegant. Is he just fixing one final correspondence? Now, this is demonstrating something very important, that it is possible to learn in these spaces where you've got a very complex model and very few data. But the reason you can do this, that he's going outside the regime of the data there, but it extrapolates in some interesting way. The reason you can do this is because you're properly handling the uncertainty in the model. So you're using probability. This is another example where he's doing it with images of insects. So I've tried to skip the bit where he solves the correspondence. But he's got 4 insect drawings here. He's got the correspondence, and he can just move around generating these interesting variants. Notice it doesn't understand constraints. So the bits where the limbs join the body, it doesn't have that as a fixed constraint. It's just using data to sort of learn that constraint. And what he's doing here is he's set the interface up so that he can click, stamp, and then move in the latent space to, or just rotate the animal. I think it's randomly sampling from the latent space to generate these little animals. So I've been utterly convinced that in this low data regime, this model is, it's extremely performant. It's widely used in, has been used in tracking and animation, various things. Of course, the arena we're in now is more big data, massive data. I've got so much data, I don't need to have those things. You might think, well, are the days of that gone? I think absolutely not is the answer. Absolutely not. All that's going on at the moment is we're knocking down all the applications where there's an enormous amount of data available. Language, vision, label data. People put a lot of time into labeling that data. We're going to hit a problem when we get through those applications and into domains where there's less labeled data available. And one of those application areas, I think, is there's so little data available that what I think really interests me is this regime is when big data is small. So even if I have millions and millions and millions of data points, the actual system I'm interested in is so complicated that I'm still in the situation that Bill was with these drawings here, like 4 drawings to build the whole thing. And I think that that's the area where that's the area we've been targeting, and we'd like to try and provide some solutions. So generalization with much less data than dimensions. Okay, I can give you the theory as to why that works. Basically, the cursor dimensionality is an overplayed card, I would say. And this model totally avoids the cursor dimensionality. In fact, the blessing of dimensionality with this model, the higher the dimension, the better things get. And nonlinear models can be used with, there are fewer data points than dimensions without overfitting. So this is the domain. So 2 aspects to this picture. Number 1, this is the reality of that snake I showed you at the beginning. It's a medical snake here. But the medical snake is climbing up. So it's not eating itself. We're making progress as we revisit these ideas. So the thing I want to emphasize is it's brilliant that we're revisiting these ideas because we're bringing so much new stuff to them, and we're also making progress. But the other reason for introducing this slide is that I think that this is a really interesting domain. So this is a Marie Curie ITN project that a few groups in Europe have, including Jean-Philippe Vert, Carsten Borgwart, many others I'm forgetting, where we're interested in using machine learning in personalized medicine. Now, in this domain, I think there are particular problems. And those problems are what I would call massively missing data. We tend to think of missing data as being, oh, I've got a table, and then I'm missing about 10% of the values in that table. And that's a missing data problem. That's not the reality of missing data. The truth is you were missing 99.9% of the things you could know about any problem all the time, more than 99.9%. So I sometimes use this example. I sort of say sometimes, well, my mum, she drives a Hummer. Everyone knows what a Hummer is, right? Yeah? So if I say my mum drives a Hummer, you are all starting to think things about my mum because she's driving one of these enormous American 4x4 vehicles. So you're thinking, is Neil's mum a Hollywood movie star? Does she perhaps, is she a drug dealer or something like this? What is it that she does? You're all thinking terrible things about my mum, and therefore things about me as well. Now, you're capable of doing that because you're sort of human. And what you're doing is you're building, I don't know, somehow on the fly you're constructing a model for what that means about my mother, even though you didn't know I was going to say it. Now, so in that sense, this idea of a data feature is a bit of a misnomer. the data feature set can change at any time, and the nature of the data can change at any time. And we don't even know what we're going to see. The missing data problem is so severe, we don't even know what we're going to see. There's an infinite possible number of additional features we could see. Now, actually, my mum drives a Volkswagen Golf, which makes it rather less interesting. She's just like a lot of other people's mums. But the fact that you can assimilate this information, and you will do it with the correct level of uncertainty. You don't immediately assume this stuff, but you take notice. It shows how important these sort of massive missing data things are. Now, in a medical domain, these sort of things could be medical tests that we don't even know exist. So we need to be able to deal with that type of scenario. So normally, we tend to impute things with expectation maximization algorithms. But in this domain, this just doesn't work, because in the EM, you normally make an initial guess for the missing data, then you update the model parameters according to your initial guess, and then you update your guess of the missing data given your model parameters. Now, if you do that sequence, but you're missing most of your data, your model that you fit just fits to rubbish. So you never get out of it, you just make bad guesses, you keep making bad guesses for the missing data. You don't really want to do that. What you want to do instead is, so for these this is EMIS is a data set in the UK, 39 million patients with thousands of tests. But for most people, most of those tests are missing. So you're not going to be able to guess the result of everyone's test for diseases they've never had. You have to be able to handle the missing data straight off. And the right way of doing that probabilistically is just simply marginalization. So if for a particular patient we only have two tests, PY1, PY2, then we just need to do this integral. Integrate over all the tests that are missing. Now, annoyingly, that's a high-dimensional integral and very complicated. So these tests include all tests that are not yet invented. If we're going to have some sort of monitoring system that's going to worry about our health over long periods of time, we can't just say to doctors, you can't invent any new tests, because we've learned on the why we've been given. We need to be able to handle this type of thing. Now, that is a horrible integral, pretty much for every distribution, apart from the multivariate Gaussian. And that's actually why Gaussian processes are so important. So if this is a sample from a multivariate Gaussian, a 10-dimensional sample, if I want to know the marginal, and this is the covariance I sampled it from, if I want to know the marginal distribution of two of these tests, P1 and P2, it's very easy. I just need to find the covariance associated with those two tests. So the reason Gaussian processes are very powerful and useful is because they have this marginalization property. And it's being exploited across all the sort of work on Gaussian processes, but it can also be exploited to handle high-dimensional data sets where many of these data sets are missing. Now, to give you a pictorial contrast, so this is, we've done work with this initially with Raquel Urtasun, but with Niccolo Fusi and Max Wiesler as part of the Marie Curie ITN work. We're trying to push this forward, using it for collaborative filtering. So collaborative filtering, the sort of Netflix-type data where you've only got a few movie ratings, there we used this trick to just marginalize over everything that was missing. Now, at the time, we had sort of state-of-the-art performance on a few collaborative filtering benchmarks, but I haven't checked back recently. And that encouraged me a lot that these models work very much in that domain. Just to contrast this with sort of the typical type of model people have used probabilistically in deep learning, if this was, what we're sort of saying here is this could be a restricted Boltzmann machine, or it could be a Gaussian process with a certain number of latent dimensions. It's just a graphical representation. Now, the interesting thing, if you have a missing data point in the Gaussian process, what I was arguing before, but just by waving hands, is basically that node just disappears. You can integrate it out, and it doesn't affect the rest of the graph. In a restricted Boltzmann machine, you can't do that. What you actually get is a deeper model. So in a restricted Boltzmann machine, if you have an observed node that is suddenly missing, that node itself, in effect, can just be pulled up to the layer above, and you've got a deep restricted Boltzmann machine. If you keep doing that with many, many nodes, you find that you get another layer above. So that model, it's not very suitable for this domain, which is another sort of reason to go into Gaussian processes. So how many additional latent variables should you have for massively missing data? Well, in a Gaussian process, what you can show is the answer is infinite. You have infinite potential missing latent variables, and the model is consistent. That's what makes it a process. You can't do that with the Boltzmann machine. Okay. So this is a class of models that interrelates the data but allows for a variable observation of P, new P's that come all the time, P that behaves like N, it just appears out of nowhere. And it's using this common assumption that the high-dimensional data lies in a low-dimensional manifold. But what we'd like to do is be able to retain the marginalization property of Gaussians, but deal with also non-Gaussian data and data that isn't drawn necessarily from a Gaussian process. The Gaussian processes are very powerful, but they do have limitations. So what is a Gaussian process? I've talked about them a lot, and I'll have a one-slide sort of review. So probabilistic modeling, I don't really like the term Bayesian because it makes us sound like a religious cult. Bayes also did very little on the domain. It was, all the interesting stuff is done by Laplace. And as an Englishman, you can see I'm biased in saying that. Laplace is really, really interesting to read on it, actually, even today. If you, certainly in English translation, I can read a little bit the French. But the basic idea in probabilistic modeling is that instead of optimizing over parameters, you have a way of sampling across those functions in this case that are giving us that mapping from the low-dimensional to the high-dimensional space. Here, this is one-dimensional input, one-dimensional output, and these are samples from a Gaussian process. Now, we can create many, many, many samples, and the idea is we combine them with data by throwing away samples that don't go near the data. That's the process of probabilistic inference or Bayesian inference. This is the prior distribution over functions, and this is a posterior distribution over functions. The nice thing is we retain this uncertainty in the posterior distribution over functions. So something I didn't show you, or well, to be honest, Bill Baxter didn't show you in that demonstration earlier of fitting the faces, is that you have uncertainty in those regions where you move away from the data. So he was using 4 data points in 2 dimensions. So he would have had quite significant error bars, and he was just showing you the mean function, but he could have given you the error bars as well. So you're considering all possible paths through history. So I think that this is really interesting for me. People like to provide narratives for how events came about, and everyone has their own personal narrative for what caused things to come about or what caused their life to come about. But actually, I think the truth is that these narratives are often incorrect and often uncertain. So there's a family of narratives for how things came into being. And each narrative is personal to what everyone's personal data point is. And I kind of think that you need to reflect that sort of uncertainty in your modeling. Certainly, if you want to be in this regime where you don't have much data relative to the complexity of the model. Okay, so they're closely related to kernel methods. So the kernel, so there's, actually, if you know about kernel methods, K is the covariance of the Gaussian process. You basically end up with a posterior mean and a posterior covariance. I don't want to go through that. If you want to know more detail about these, I kind of think that you shouldn't actually be allowed to work in machine learning unless you know what a Gaussian process is. That would be my rule. There would be a test on the door of the conference. But not many people seem to know what they are. They are super fundamental. They cover a large number of different algorithms. And I decided rather than imposing that rule, we'd start this series of summer schools. So if you do want to know more about them, or we've also got lots of videos on the web to see about them. But I kind of really have enough time to talk so much about that now. So why deep, though? Well, I love this idea of nonlinear dimensionality reduction. And the original idea for going, I think a lot of these thoughts come out from ICML conferences. I think this one in Pittsburgh, I don't remember which year that was, but a conversation with Kevin Murphy where we're talking about, I was saying, well, no, surely we should be modeling high-dimensional data by looking at a low-dimensional manifold. It works really well, as you've seen. And Kevin's like, he was into sort of probabilistic graphical models. He said, no, we want to model conditional independencies between the data. And I kind of think he's absolutely right, but I'm right too. And of course, the truth is you want to sort of do both. So what do I mean by conditional independencies? Well, I might exist on a low-dimensional manifold, but I can move my arm conditionally independent of my other arm. I can sort of operate these sort of things together. So you kind of want some hierarchical structure that pulls these things together. And that's sort of what we ended up doing at ICML in 2007. Stacking these models. And this is very much inspired by a talk by Geoff Hinton at Microsoft, which must have been like 2001 or 2002, where he was stacking the RBMs. So we sort of thought, okay, let's stack these GPL VMs. And the idea here being, for example, these are 2 subjects in motion capture data walking towards each other and high-fiving. The model works very well in motion capture data. And what we did is we got one latent variable model for one subject and one latent variable model for the other subject, but then you can train on top of that another latent variable model for them both. How did we do this training? Well, initially we copied what Geoff had done, which we did greedy training, greedy layer-wise training. But then we actually found out we could backpropagate through the whole model. So we backpropagated through all the Gaussian processes. As long as we had a strong prior at this top level, which turns out to be a time-based Gaussian process, that worked. So, and this was an ICML paper back in 2007 that was doing that. The problem with this was that we couldn't learn the structure. So we did it in these domains, like this is a domain that I was, well, still am quite interested in, human motion. Because this inspired some of these thoughts. In fact, they're also very much inspired by a talk by Michael Blacker, ICML in Banff, 2004, the bag of the, I don't know, there was some, I can't remember what he called it, loose-limbed trackers. And that was all about conditional independencies. And this is kind of trying to combine those ideas. So you've got conditional independencies in this model here. This is the structure. So you've got a separate latent variable model for each of the left arm, the head, the right arm, the abdomen, the left leg, and the right leg. And then you have some model for controlling the part of the upper body, the head and the arms, a model for controlling the lower body, and then it turned out this model was best on the abdomen up here, a sort of controlling overall model. And this is the sort of results we could get, and actually what you can do is you could operate by moving in the latent space here, and you could move one arm, and then you could operate by moving up here, and then everything coordinates together. So that was really nice, but we didn't sort of push the work further because we imposed the structure. So we felt we had a handle on what the conditional independent structure was on the human body, and we just imposed that structure. So the recent developments, so first of all, we don't call it hierarchical GPLVM anymore because it's much more sensible to call it deep Gaussian processes. But the other thing we changed is we can now learn the structure of these models. So we build deep Gaussian processes, but because we're integrating over all these functions, we can actually learn the number of latent variables in each hidden layer and the depth of the hierarchy. So that was what that slide says. They also have some really interesting mathematical properties. So another way of looking at what we're doing is actually this is a composite multivariate function. This is what all deep models are doing. And this is the sort of thing that when you look at this, you just say, well, why are you doing that? Because any mathematician will say, well, you're just creating a function. Well, I think what's very important becomes very clear when you're working with Gaussian processes is, yes, you are just doing that. This is kind of a meaningless thing to write down unless you start specifying the properties of the functions on the right. What you're actually doing is changing the properties of the functions on the left by building up from simpler units of the functions on the right. Now, when you see it as a probabilistic process, so when you see this model as a Gaussian process, you can start talking about the statistical properties of this function on the left. So, what is the nature of that process? So one of the nice things, so David Duverneau and collaborators did some work where they looked at this and sort of said, well, you can start talking about properties of the derivatives of this function. So one of the properties of a Gaussian process, so if each of these is a Gaussian process, you know that the marginal distribution of the derivatives at any point is Gaussian. So if you want to know sort of how your derivatives are, they're Gaussian. That means that you're never going to get a discontinuity, and that's something that Gaussian processes won't generate. Certainly they won't generate in a non-parametric way. You can get them to generate them parametrically, but a discontinuity. Now what David and collaborators showed at AI Stats last year is that for this deep Gaussian processes, you can show that you can get sort of heavier tail derivatives. You change the property of the stochastic process. Now, this isn't actually a property that we were looking for when we started working on deep Gaussian processes. We were much more interested initially in these conditional independent structures and these arguments that, that you make by going, oh, there's abstract things and there's detailed things like this. We like that sort of thing. But you can sort of look at theory around it. So what we're interested in is sort of extending this idea to compose these processes with things like Indian buffet processes or infinite binary processes. So we get a fully non-parametric, very flexible class of models. There's another paper, I'm not sure, actually I meant to check with Yarin where they're aiming to present it, where they show that dropout is a variational approximation to deep Gaussian process. I have to thank Max for pointing this out to me yesterday, and I read it last night. And they're showing that actually dropout in a neural network can be shown to be approximating a deep Gaussian process. And one of their claims is the reason you don't tend to get overfitting is because you're using the framework of deep Gaussian processes in order to prevent overfitting. So what do these sort of things look like? Well, one motivating thought I had is, well, this is actually, I think, the slide that inspired David to do the analysis, because these things look pretty funky, and they're kind of funky for a reason. This is sampling through multiple Gaussian processes. And the thing I was trying to illustrate, although David saw a different thing when I did this, is that once you've got one feature in here, you never lose it. So it's actually buried in here now. It gets buried a bit. It doesn't get buried at the dimensionality. The problem is you're looking at a two-dimensional projection of something that could be in much higher dimensions. The features don't get buried in that case. They certainly do in these, when you keep looking at these lower dimensional projections. But if you sample from this model, so this is like a square that I'm putting through a Gaussian process, through a Gaussian process, through a Gaussian process, through a Gaussian process, the things that come in at the top stay there forever. And then they're propagated right through down to the bottom. And the idea with this thought was, okay, this is like this idea of abstract features, more combination, low-level features down to data space. So this, with Andreas Damiano, who did all the implementation on deep Gaussian processes and loads of other great work, a PhD student of mine, a postdoc now, we sort of wanted to say, well, is this what actually happens in practice when we start looking at data? So we build these sort of deep Gaussian process models to learn in an unsupervised way. Do we get this abstract features down to more detailed features? Now, we do have problems with, sorry. I forgot that I was just going to show this again. Pause, rewind a little bit. So the first thing we wanted to do is look at whether we could learn the structure. So revisiting that experiment from ICML in 2007, one of the things Andreas did with the model that can learn the structure is this. So he rebuilt the model of the two people doing high fives, but he now told the model you have to learn your own structure. So whereas before what we built is we had one two-dimensional node over two two-dimensional nodes going down to the data, the structure actually learned was one two-dimensional node going down to one two-dimensional node that is shared between the two data, and two-dimensional nodes that are private to the data. So it's saying actually most of the stuff going on here is shared. So that's nice that we can get this structure learning. But notice it's quite low data. The other thing we looked at was whether we could justify deep hierarchies for very small data sets. I was trying to work out how to include this here. I couldn't think of a good way of explaining it very quickly, but the deep models are actually less complex than the shallow models when thought of in the statistical sense. They're more complex in the modeling sense, in the other way I use complex, but in the statistical sense, they're less complex. And the interesting thing was, could we take 150 digits? Because you don't see normally deep learning being applied to very small data sets. And would it justify, we can learn the structure. So would it learn a structure of a model that was deep? So Andreas trained on zeros, ones, and sixes from, I can't remember, was it USPS or MNIST? And indeed, it did. The model with the best marginal likelihood, or approximation to the marginal likelihood that we make, is the 5-layer model. So we required 5 layers to model this data. And we also switch off variables in each layer. So these sort of, what we did is, what you can see here is W5 is, we have weights, one weight associated with each node for switching off the variables in each layer. And what you see is blue ones are ones that switched on. So we gave it initially 1, 2, 3, 4, 5, 6 to work with, but in the top level it uses 1. If it's very high, it's a very non-linear node. If it's very short, it's a very linear node. So it's using sort of 3 linear-ish latent dimensions and 1 very non-linear latent dimension. And then 3 non-linear here, 1, 2, 3, 4 non-linear here, and then, but this bottom layer uses a lot. What Andreas has then shown on the left-hand side is he's shown what happens if you, in one of these dimensions, you can find a place where you're generating the shape. We're looking at the mean function again here. And here he's found a place where as you move in that dimension, what you get is closure of the 0 at the top. Bear in mind this is only 150 data, so you actually get something else going along. It's not enough data to know all the independencies of these details at the bottom. If you do the same trick at this layer here, so you find Andreas has found a point in this 1, 2, 3, 4, 5-dimensional space that generated this 6, and then he's moving along one dimension, and that dimension causes the bottom of the 6 to open and close. At this layer here, he's found a place where you can start with a 6 and you move in one dimension and you change towards something that looks more like a 0. And then at the top layer here, in this dimension, he's found a way of going between the 0, the 6, and the 1. So it really does seem that the model, even with 150 digits, it wants 5 layers. It didn't want 6, it selected 5. It selects the actual dimensionality of each layer, and deep learning is important and justified, and you get these abstract features out at the top. So why are we doing this all? Well, this is the sort of long-term vision we have. We'd love to integrate lots of information about patients, including social networks and clinical notes, all into one model so we can do a much better job of predicting survival, predicting what the right treatment should be. The way we're doing this at the moment, if you look at a lot of papers from my group, is they're taking like 3 parts of this model. So we've done genotype, environment to gene expression as one paper. Well, actually, we've got 3 papers on that. Alan Saul, a student of mine, is working on survival analysis. The nice thing with Gaussian processes is it's a very statistically well-founded model. So you can take information from a survival modeling community, you can combine it properly with the Gaussian process, and then combine it within the Gaussian process framework. Of course, for any given patient, loads of this information would be missing, and so it's vital to be able to handle missing data in this context. So that we call that deep health. Okay, and then there's some references at the end. That's it. Thanks.
Yes. Thanks for the very interesting presentation. I want to comment about some of the similarities and differences between what you've done and what many people have been doing in deep learning. So what you have incorporated in the Gaussian processes is the preference, or you might want to call it a prior, that you want your final function or distribution to be obtained as a composition of simpler ones. And clearly this is one of the important attributes of deep learning models, and there's some theory about why you could have a statistical gain if that prior is, works well for the data, of course. But there's another prior that you're missing. Well, at least one that we find in most usual deep learning models, which is the one we call distributed representations. So each of your layers is a Gaussian process rather than being some kind of factorized type of distribution or a set of features that can independently take different values. And both of these actually bring an exponential advantage in terms of statistical the number of examples you would need in order to get some generalization error if the data fits those assumptions. It would be nice if you could find a way to incorporate that other prior. And just to conclude on this, initially you talked about simple and complex, and I find these maybe a little bit difficult to really make sense of. I like to think of that our models, using your interpretation of the word model, correspond to making assumptions about the world, and some are not restrictive at all, like the smoothness assumption that you normally have in Gaussian processes, and some are slightly more restrictive, like the distributed representations or the depth. And the more restrictive they are, of course, the potentially more they can buy you in terms of generalization, assuming they are appropriate. And now, that's just that comment.
Yeah, so just thinking about the first point, I think that's interesting, actually, and it gives me a chance to plug our poster. So Zhenwen Dai has a poster on, looking again at the hierarchical community of experts. Does anyone remember this model? So it's a model where you've got a sigmoid belief network switching in and off linear models. It's from Geoff and Zubin and Brian Salons back in about 1997. And I think one idea is for different data, could you have a different switching network pulling in different parts of the model? So you can see that as a sort of deep Gaussian process, but the Gaussian processes are all linear and one-dimensional. But so we're kind of moving in that direction. And I think the Indian buffet process stuff might be a move in that direction. The second one, the simple and complex are bad terms. I think you could probably spend an entire talk on trying to get that point across well, and I may not have done it. I guess the thing I really mean is in low data, I'd rather use a Gaussian process. Yeah, don't know if that's a good answer.
Neil, can you sketch for us how inference works? What kind of algorithms underlie these models?
Yeah, that's I actually think, and I should have mentioned, I think there's some really nice work coming. Max Welling, Durk, Kingma, and Danilo, and Shakir, where they're doing these type of models with neural networks. And I think we're learning a lot by looking sideways at that and going, hey, they're doing these inference methods that are very different to ours, and they seem to work well there. I wonder if that would transfer. But the nature of the inference method we're using is something we call variational compression. It's based on an idea by Michalis Tsitsias from 2009, and it's I'm going to talk about it at the large-scale kernel machines workshop, the first part of it. But it's complex, and the challenge is scaling it. So we'd like to work on scaling it to do hundreds of thousands, millions, billions of data. Yeah, I'll talk about that later at a different workshop.
So in your argument where you use the Boltzmann machine to argue that you should marginalize, so the Gaussian process is so wonderful because it automatically, marginalizes. If you take a directed network, I mean, don't you have the same property, even though it's not, a process?
Yeah, there are other networks where I think it's less of a problem. Yeah, that's true. I was obviously not emphasizing those other models. I think, yeah, that's true.
Okay, let's thank the speaker again, and we'll be back in half an hour.